Hello everyone, I'm Mojtaba and welcome to another episode of A Sip of Chemistry. Today you'll be hearing from James Shelby, a legend in glass science who has both academic and industry experience on his resume. He obtained his Ph.D. in ceramic engineering from the University of Missouri in 1968, then joined the technical staff at Sandia National Lab in Livermore, California. After 13 years of tackling glass-related challenges in industry, he transitioned to academia to pursue his lifelong passion for teaching. His research interests cover a wide range of topics, but he is particularly well known for his expertise in gas and water diffusion in glasses and melts, which earned him the prestigious Morey Award. However, he believes the most significant contribution to the glass science community is his book, Introduction to Glass Science and Technology, a valuable resource for undergrad students. Though he is retired now, he remains busy writing a book on germanate glasses, which is expected to be published sometime next year. It was my honor to have a friendly conversation with him, discussing the past, present, and future of glass science. Please stay tuned and enjoy this exciting interview with Professor James Shelby. Thank you so much, Professor. Thank you for your time. I'm so excited to have this conversation with you. Thank you for sparing your time for doing this interview.
Oh, no problem. I'm happy to do it.
Just usually, as always, I would like to ask at the beginning about your academic background. Where did you go to university and get your degrees?
Well, I went to, at the time I went there, it was called the Missouri School of Mines and Metallurgy, which then became the University of Missouri at Rolla and is now Missouri Science and Technology University. So it's changed its name a number of times over the years. And that's where I majored in ceramic engineering and had my first introduction to glass science through being taught Intro to Glass by Dr. Delbert Day, who then became my master's and Ph.D. advisor. So I got all of my degrees from Missouri School of Mines.
You already mentioned you worked with your supervisor. Uh, what was his name again?
Delbert Day, he's
Okay.
well known. It turns out he was only 7 years older than I was. I was his very first Ph.D. student. And he, of course, went on to become extremely well known in the field of developing glass microspheres for cancer treatments and other medical applications, and founded the corporation MoSci Corporation there in Rolla.
How did you become interested in glass? Why, at first place, you decided to work on this topic, on this field?
One of those sort of luck things. I'd had Intro to Glass and Glass Lab as an undergraduate. And when I was looking at going to graduate schools, I was actually thinking about sort of favoring electronic ceramics as an interest. But Dr. Day received a grant from the Army Research Lab to study the internal friction of mixed alkali silicate glasses. And he had money for a full 3-year fellowship, which he offered me at the time, and I accepted it. And that's how I got started in glass. And I've always felt that was the smartest decision I ever made in my life.
1968 to 1982, I guess. You worked in Sandia National Lab. So, what was your responsibility over there?
Okay. Well, first of all, Sandia has 2 labs. The main lab is in Albuquerque, and they had a whole group of glass scientists. I was actually in Livermore, California, where I was the only person in that lab of 1,000 people, but I was the only one with a glass background. So I was the glass specialist. So I had both my own research areas, and I was also sort of the jack of all trades for glass questions in general. At that time, started into gas diffusion in glasses, which continued throughout my whole career. The interest at that time was that they had a lot of issues with vacuum tubes. This is the old days before solid state electronics. And one of the problems with vacuum tubes is helium in particular diffuses through glass, and they cease to become vacuum tubes and become gas tubes, which means they stop working. So one of my primary responsibilities was to both make measurements for a lot of the kind of glasses we were using, but also to try to understand what controlled these factors and what we could do to change them to improve the performance, etc. At that time, I actually got interested in phase separation in glass, which became another major item in my career because we discovered that one of the glasses, a borosilicate, was very low helium permeability when it was manufactured, but in converting it to vacuum tubes and all the heat treatments, we developed the phase separation. And once it became phase separated, the permeability went up orders of magnitude. So if you look at the base glass, it was great. If you look at the vacuum tube, it just wouldn't work anymore. So I got started with gas diffusion at that time. My other major responsibility in the later years there was in solar energy. This was when the country was first getting into really emphasizing solar energy. Sandia became one of the leaders in that field. And we were actually building a solar facility, a pilot plant there in Livermore, which involved float glass mirrors, which all focused to a tower, where the heat that would heat the material in the tower, which was then generate steam and drive turbines. And actually, they built a plant in the Mojave Desert outside of LA, which I think is still in operation. It's been expanded a number of times, which primarily provides peak power. So it's used when LA needs more air conditioning. It comes online. But that got me into the solar energy applications, and which I followed up on also throughout the large part of the rest of my career. It also introduced me to a number of people in the glass science community who became colleagues and friends throughout the rest of my life. People like Carlo Pantano from Penn State and a number of others, Bob Doremus, and other people like that. So those were my two main responsibilities. I was lucky because being the only glass scientist there, my supervisor really didn't know what I was doing most of the time. I was able to just do a lot of things in research just because I was interested. And that's how I got into working a lot with borate glasses and germanate glasses, and was able to do a lot of work with phase separation and other sort of basic glass phenomena.
Awesome, amazing. So, phase separation, what was your tool to investigate the phase separation in glasses? What was your approach?
My approach was a little different from most people. Of course, use electron microscopy and so on to study it. My approach was to look at its effect on the properties of glasses. And I've published a large number of papers in that field. I personally feel that, I was looking at how it affects TG enormously, of course. And it affects anything to do with transport, gas diffusion, electrical conductivity, chemical durability. Most people don't realize that. Why is Pyrex, standard old Pyrex, so durable? Well, the reason is because it's phase separated. Because essentially all the sodium and boron is locked up in the droplet phase, and the matrix is almost pure silica. That gives it a much higher durability than it would be if it were homogeneous glass. I really feel I almost became a crusader about phase separation because I feel that a lot of the people working in glass who come from, say, chemistry or physics backgrounds, other backgrounds, they've never been introduced to the concept of phase separation. It's rather foreign to them. And they're not really aware of it and how common it can be in glasses. And I find routinely, for example, I just read a paper this week on some sodium borosilicate glasses with an NMR study. And half the glasses they were looking at are right in the middle of the phase separation region. But they interpreted all their data on the basis of these being homogeneous glasses. And thus they were very surprised to find that there were more boron-oxygen-boron connections than they would have expected. Well, of course, because one of the phases is a high sodium borate glass. The other phase is a high silica glass. So what they're seeing is the average of all of these things. And if you don't understand that it's phase separated, you completely misinterpret the data. And I still see that happening a lot in the literature. But the effect on properties is something I think is understood. It's not as understood nearly as broadly as it should be throughout the literature.
It's a big deal, because glass in glass phase separation, it's not easy to understand, right? It's a crystalline phase separation. XRD can tell you what's happening, but in the glass, yeah, it needs expertise. Eventually, you left SNL and joined Alfred University, right? What happened? What was the story about it?
I always tell people I didn't really leave Sandia. I went to Alfred. I was very happy at Sandia. I had a great job. I liked living in California. It was, everything about life was really very good. But I'd always wanted to teach. And when I graduated, got my PhD and went to Sandia, my intention was to be there 5 years. And then I'd start looking for a job at a university. Well, that turned into 14 years for all the reasons that life happens. One being that there was a good period there in the 60s when jobs were not available at universities. We were in sort of a recession and so on. And I'd actually stopped really thinking about it. And I ran into David Pye, who was a professor, the senior professor in glass at Alfred. And he asked me if I was still interested. He knew I'd been interested potentially in this. And he told me they had an opening. And my first response was, no, I don't think so. But an hour later, I realized why. That's what I want to do. And I went up to Alfred to interview and spent the next 26 years of my life there. So it was like so many things in life. It was a chance meeting. We were just sitting in a bar, having a beer and chatting about life and glass and so on. And he said, oh, if you're still interested, I think we're going to have an opening coming up. And that's what happened. So, and it's one of those decisions I've never regretted. I've always thought it was, again, one of the best ones in my life.
What was your research activity in the Alfred University?
Well, they were obviously very broad. When I first started out, I was sort of continuing things I'd been interested in at Sandia. I was lucky in that I was able to bring my gas diffusion permeation measurement equipment with me from Sandia. It was technically a loan, but I kept it for 10 years before I returned it to them. And so I continued to do work in that area. And the same thing, I broadened my work out into much more work into the properties of glasses. My first NSF grant was on the role of gallium oxide in glass. And I had a couple of PhDs in the area of alkali gallium silicate glasses, and continue with that. The idea of gallium versus aluminum is, I've got a long list of interest, but that's always been one of the items that I was interested in. Over time, Alfred got together, the professors at Alfred put in an application to NSF to form a Glass University Research Center. Or, I'm sorry, a Industry University Research Center for Glass, sponsored by NSF. And Dave Pye headed up that operation. And we actually eventually wound up with over 30 companies as members of this. And they funded a large variety of graduate research there. At that time, they were beginning to look into the concept of going to oxygen-fired as opposed to air-fired burners for glass melting for the commercial tanks. And one of the early things people realized was that meant that the water content in the furnace atmosphere was going to be much higher. Because when you use air, of course, you're diluted by all the nitrogen in the air. When you use pure oxygen, that you don't have the nitrogen there, which is the reason for doing it, so you're no longer producing nitrous oxides. But that also means you have much higher water content in the melting atmosphere. So there's a lot of concern about what's that going to do to us? What's it going to do in industry? To float glass, to bottle glass, to anybody that makes bulk glass. Back then, there were TV tubes. I don't remember cathode ray tubes. And they had lead glass and other glass and all in those glasses. So there was a wide variety of interest in this from the member companies. So they sponsored work for a number of students, and the water solubility and diffusion in glasses and its effect on properties. And we were able to show, for example, that with things like float glass, the annealing temperature used dropped 7 degrees once they converted to oxygen fired, which means they can lower their annealing furnaces by 7 degrees. It doesn't sound like much, but when you make 100,000 square feet of glass a day, you've got a lot of energy going into those annealing furnaces, and a few degrees at the top end makes a big difference. One of the other things that we discovered was that in borosilicate glass melting, that water vapor increases caused enormous losses of boron. It just sucked the boron right out of the melt. You can lose half your boron, which you can imagine, of course, destroyed the product. So eventually, the borosilicate industry was able to compensate for that. They overbatched with boron and other techniques, which I was never privy to, which of course were proprietary. But so a number of things came out of that. My own interest really, of course, was just the science of it. Was, what happens? How does glass composition affect it? We looked at silicates, borates, germanates. So that's how we got into the water diffusion. And of course, we had kind of stopped doing permeability of helium and inert gases. And we got much more into doing solubility, which was a totally different kind of measurement. So that's where we got into a lot of the helium solubility work we did. I had a postdoc named Melissa Mesco who just did fantastic work in both of those areas over the 2 years that she was with me. and we published quite a few papers in that area. And throughout all of this, I always continue just working on various things in phase separation effects on properties, just properties of just weird glass systems, or ones that were less, shouldn't say weird, but less commonly studied. Things like like tungsten and the rare earth elements and other things, gallium, scandium. And that eventually led to a book I edited called Rare Elements in Glasses, which was all chapters about the rare elements, the less studied elements in glasses. Last year, as I was there, I became very interested in the idea in looking at metal colloid production in glasses. Started with the simple ones, silver and copper, the common ones. And then we eventually got into things like nickel and cobalt, which we found we could actually make solid solution alloys, which would vary the Curie point, say, but they were magnetic, ferromagnetic, because they contain tiny particles of nickel and cobalt, which are, of course, very magnetic. But by making alloys, we could vary the Ferri temperature over several hundred degrees. I mean, the Curie, what am I saying? I'm 81 now. Sometimes the words come a little slowly, which is an interesting thing. And so we continue doing a lot of work with metal colloids, indium colloids, all kinds of elements that had not been studied really. The other thing that we were doing was we received some grants to look at hydrogen storage in glass microspheres. We found that if we dope the microspheres with elements that would absorb in certain wavelength ranges, if we would shine a light on them, the gas would go in and out very fast. At the time, we really didn't understand why. Toward the very end, we finally realized what was happening was we were making these microspheres so strong absorbers of infrared that they would heat, say, from room temperature to 300 or 400 degrees C in about 1 second. They're no mass. I mean, they're so tiny. They're hollow, and they were filled. You could fill them with hydrogen, and you could control the hydrogen release then by simply controlling the intensity of the light. When I left there, that work stopped, and the U.S. has sort of lost interest in that idea. But if you look at the Chinese glass literature, you'll find that there's still a very active effort going in China on storage of hydrogen glass microspheres. So that was those two, colloids and the microsphere work, were sort of the last things I did before I retired.
Amazing, amazing. It's been a lot of work. Yeah, that's amazing.
I was always interested in a very broad range of things. I always said, there are two types of people in glass, two types of scientists. They're the ones that have a technique, like a person who does NMR, and they do it extremely well, and they study a lot of different glass compositions, but they're what I refer to as the methods people. And then there are the people that, like myself, that are more interested in certain kinds of compositions. And what we're interested in is studying everything we can about those type of compositions. Like with gallium, we've done everything from the properties to NMR to XFs, Raman, infrared, you name it. We've studied it. Germinate glasses were sort of that way. They were always a hobby of mine, a sort of a personal interest. And I sort of did the same thing. So I always consider myself more of a materials type person as opposed to an instrument type person. And I think you still will find that that's sort of a breakdown you can do with glass scientists even today.
In addition to a few hundred articles, you also published a book in Glass Science, Introduction to Glass. I think that's the title.
Introduction to Glass Science and Technology.
Yeah. That's one of the highly cited glass books in the academia. There are so many glass books in the market, but it's still actually very well used in the academia. What's first of all, why you decided to write this book, and what's make this book specific?
Okay, that's interesting. Um, I was just last summer. I went to the boron glass. This is a little background. I went to the boron glass conference in up in Corning, New York, which was the first conference I'd been to since I retired. So it'd been like 10 years since I'd been to a meeting. And there was a whole new group of graduate students there from a lot of schools and people I'd never met. And I found that so many of them came up to me and wanted to comment to me about that book, which when I was actively working and the book was out, but nobody ever said anything about it to me. All of a sudden, it was just all these people asking about the book and how I came about, and telling me how much they liked it, and had gotten from it, which made me feel very, very good about it, because that's why you write a book. You want people to read it. It came about through, again, one of these just chance circumstances. The Royal Society of Chemistry, who published it, actually contacted Alistair Cormack, who was British but was a professor at Alfred, and asked him if he knew anyone who would be interested in writing an introduction to glass book. And he came to me and asked me, and I said, sure, why not? I had a sabbatical coming up, and I used that sabbatical to write the book. One of the things I did, and the reasons I think it is proven to be quite useful, is that I had always found that most textbooks were written for other professors to impress your peers. Well, I don't think an intro book should be written for your peers. I think it should be written for the students. So one of the things I actually did was I hired some of the undergraduates I knew who had only had intro to glass, no glass courses beyond that. So they didn't know, they knew enough about glass to give a judgment, but not enough to actually know much yet. And I hired them to read the chapters as I wrote them and give me feedback. Because it's very easy when you start to write a book like that to start to write it at the level of your own peers, and not and not to remember who it's for, that it's for the student. So I tried throughout that book to write it for the student, to be understood. And I think I was pretty successful in doing that based on the response I've had over the years. It's on its third edition now. It's been in publication continually since 1995. So that's close to 30 years now. And it still sells a couple hundred copies a year. I don't know for sure what schools use it, anymore. But I do know that there's a surprising number to me of schools outside the United States where it's used. And I find that you're right. I get notifications when my papers and books are cited from Science Direct. I think a lot of people are familiar with that. And I get 2 or 3 notations a week saying that Intro to Glass Science has been cited in this paper or that paper. But I think that's why it's been so successful, because it was written for the person who's trying to learn about glass, not for the person who already knows about glass. There are the books for them.
Okay, yeah, amazing. I like the book, and I've read it. Not all of them, most part of it. The introduction part, the principle of glass formation, the effect of viscosity, and all these things. It's easy to follow, and it doesn't have big equations. Usually, we see in glass textbooks, which relates the property to viscosity and all these things, or the glass making ability to viscosity.
I've actually found out just through, odd contacts that although I never receive a penny of royalty from them, that the book has actually been translated into Chinese and Russian and is published in both those countries. I'd love to see a copy of one of those because I'd like to know, for one thing, if my name's even on it, or whoever translated it just put their name on it. Sometimes China and Russia are not noted for following copyright law very closely, you know. But that's also rather, I don't know. That's, even though I don't get any royalties from it, I never made much royalties off it anyway. You do not make much off a book on glass. But just knowing that, okay, it's actually somebody bothered to translate it, it's still a little bit flattering when you come down to it. So I think if you ask me ultimately what's probably the greatest contribution I've made to glass science, and even with all my research and so on, I suspect I'd say that book, because it's influenced so many young glass scientists and engineers over the years.
Yeah, that's a great book, a useful book for undergrad students. You are still active in research and writing a book on germanate glasses. So tell us more about it, please.
I'm obviously not active in lab research anymore since I live in New Jersey now. Not a lab anywhere around, but that's been over 10 years. My research now in general consists mostly of just analyzing a lot of published data and looking at trends, and I still publish a few papers now and then on some things that just never got published for one reason or another. Some of it's maybe kind of old, but since nobody's done anything about it since, it's still new to the community. I started, my interest in germanate glasses came about way back when I was in graduate school. Would have been in about 1967. To give you some perspective, the germanate anomaly was discovered in 1962. I don't know if you're familiar with the germanate anomaly. It's got to do with lots of maximum. It's similar to the borate anomaly.
Boron anomaly, I know. I guess that germanate anomaly should be something like boron anomaly, the change in the coordination number.
There are even more anomalies in germanate glasses than in borates. Virtually all properties of germanate glasses display maxima or minima. I went to my advisor, Del Day, and asked him if he'd spring for the money to buy a small bottle of GeO2, which was very expensive. And I melted a few glasses, and we published a short paper on the internal friction of sodium germanate glasses in 67. And that's where I got started with them. And it's been a hobby of mine ever since. You know, I don't think I ever had any funding for germanate glasses, but I still managed to turn out a few theses for it and a lot of my own personal work. I'd always thought for a long time about doing a book on germanate glasses, but just had never gotten around to it. After I retired, there was a period of a few years when I basically I just walked away from glass and just enjoyed being retired. And then I was approached about doing a new edition of the intro glass book. I did that. That got me back to writing a few papers and made me think, okay, it's time to do that germanate book. So I sent a book project in to the people at the Royal Society of Chemistry, the same ones who published the intro book. They were happy to agree to publish it. So I started about a year and a half ago. The book covers the structure, properties, and very briefly possible applications of germanate glasses. The vast majority of its own properties. I have a chapter on models where I analyzed the existing models for the germanate glasses, which are still very controversial. I'm not going to tell you what I concluded because you'll have to buy the book to find out. But I suspect my conclusions are going to be rather controversial in the germanate community too, but that's okay. That's kind of fun anyway. a lot of chapters on collecting all the existing literature data on properties and the melts of the glasses and putting them together, looking at the quality of the work. That's one of the things that I found, and is that in the quality of glass property data has steadily degraded over the decades since I was young. This was first noted by a Russian named Mazurin, who who put out this whole series of books in Russian on the properties of glasses, collections of all the literature data over, and developed the SciGlass database. And he was the first to really notice that the quality of glass data was going down. And I've noticed it's true too. So one of the things I did in the book was look at least the systems where there's data from a lot of people, simple things like the density of sodium germanate glasses. You know, that's probably the most commonly studied property in all of germanate glasses. And I found that the density data was pretty good. And then I looked at TG, and oh my, TG is not in a good state. TG data is probably among the worst quality data in the glass literature. It's not well reproduced. There's no standard for how to collect it. A lot of the people who measure it don't understand the difference between a quench glass and an anneal glass, effective heating rate. They don't know how to do the measurement properly. And I talk about that in the book. And I actually try to say, all right, what are really the best values? You know, I'm not fitting the data, I'm looking at it from 60 years of experience. And I know some of the people, I know the people who do really good work, and I'm not going to obviously call any names, and I don't in the book, but the people who don't do such good quality work.
I'm looking forward to seeing this book and learn more about Germanate glasses.
Well, it'll be coming out sometime next year. I don't, you know, I've finished the first draft, but there's a lot to probably about another year's things to be done before the final public printed copy actually hits the market. So,
In your opinion, what's the most important achievement in glass science within the past 100 or 150 years?
I think the most important one in history of glass, which goes all the way back, would be glass blowing, because that's what made glass something that was useful. You know, before that, they made glass bottles by a technique where you make a mold out of sand, wet sand, and you kind of do it like doing a old pottery, where you would make a strand and you wrap it around it, and then you melt it so that all fuses together, and then you scrape the sand out. Obviously, you didn't make a lot of bottles that way. Discovery of glass blowing made, well, ultimately, actually, the earliest windows were made by glass blowers. The so-called bullseye glasses and so on were made by glass blowing techniques. Containers, goblets, all the ancient Romans were using glass blowing to make drinking cups, and they find glass bottles in, you know, shipwrecked Greek ships from well before, you know, back into the BC era. And I think that really was probably historically the most single important development of all of glass, in terms of it becoming the material that is so, you know, ubiquitous to everything humans do today. In the modern era, obviously the optical fiber. I mean, we're talking over an optical fiber right now.
Exactly.
The internet would not exist without the optical fiber. And I don't think anybody can imagine what the world would be like today without the internet. I'm pretty sure that, you know, I was never actively involved directly in the optical fiber, but I was there from the first development of it. I remember when you used to go to the glass and optical division meetings, and they had what everybody jokingly referred to as the decimal derby. The decibel derby. The goal was to get the loss, the dB per kilometer, down to the point where you could make a communication fiber. And when they first started with glass, a piece of window glass, for example, comes in at around 100,000 to 1,000,000 decibels per kilometer. It's opaque. It's over, and if you make it several feet thick, it's essentially opaque. They had to go from that to something that was down less than a dB per kilometer to make the first practical fibers. And you'd go to a meeting, and the people from Corning and from Bell Labs and Saint-Gobain and other companies would give their papers saying what they had just managed to make, what their best one was. And you'd hear someone say, well, we made a glass that's 1,000 dB per kilometer. And the next guy would get up and say, we made one that was 500 dB per kilometer. Ha, ha, ha. And then the third guy get up and say, oh, well, ours is only 700, so I guess I don't really have anything much to say. And it was a competition to get it down. And of course, the people at Corning under Pete Schultz developed the chemical vapor deposition methods to the point where they could make the glass of the quality and and purity that was necessary for that. I was always interested because of the role of hydroxyl in it and the role of hydrogen reaction with optical fibers, which would destroy their transmission because it absorbed at the wavelength where they wanted to use them. But I never really worked that much, directly with them. I worked on bulk glasses in that area, but I would have to say that they were the single most important technological development. There are a few other important ones. One that's certainly for our environment is what happened with the conversion to oxy-fuel firing from air fuel in the big glass tanks, which helped reduce the nitrous oxide content of the atmosphere. Today, they're working hard to make glass melting greener, and I suspect that is going to be one of the great areas of development in the industry, at least in the next 20 years, is getting to where glass melting, which right now is not a good thing for the environment in general, bulk melting, where they can make that a much friendlier contribution to our society.
Can you tell us one of the challenges you faced when you entered the glass science and it's not been resolved? Still, it's not been resolved.
It's hard to think of anything that was really personal because I've always said that when it comes to the big things in life, I've always been very, very lucky. I was lucky to go to Rolla, to Missouri School of Mines. I was lucky to get into glass. I was lucky to go to Sandia. I was lucky to go to Alfred. If I look at glass science overall during my career time, the challenges when I first started were a lot of equipment challenges. The DSC, the differential scanning calorimeter, was in its earliest stages of development, was not widely used at all. NMR was really in its infancy. Phil Bray was just starting to do work on borate glasses. And that eventually led, of course, to the development of magic angle spinning, which has done so much to help us understand the coordination of numbers of glasses, of elements in glasses. So Raman was still, it took all day to make a measurement because they were still using high-powered lights. After that, there was the development of laser Raman spectroscopy, then eliminated the challenges from Raman and made it an everyday thing. The development of the FTIR, Fourier transform infrared. We were still working with the old IRs, which were very slow. You got to print out on a sheet of paper, and there were no computers. if you wanted to use a computer, you had to type everything on a punch card and turn it in, and you got your results back 2 days later. So computer analysis was just non-existent. So there were a lot of challenges to everybody at that, in the early days and that has certainly, the technology has developed where we can do so much more in glass science today. One thing that I will comment about, there weren't challenges to me, but I became aware of very early in my career. I graduated, I got my Ph.D. in 1968. And at that time, the glass science industry or community was male. There were one or two women, and that was it. And I found that certainly and I still think it continues today, that if you're a female coming into glass, there's still a challenge. There's a challenge to get into it. There's a challenge to be recognized for your work. There's a challenge, there's just the same general challenge that women have in most technology fields. And I have always done my best when I was a professor and throughout my career to do everything I could to help promote women scientists in glass and help them get past the challenges that they encountered that I was lucky enough I didn't encounter. And it wasn't through my efforts, it was just through my ethnicity that I didn't have to deal with those. And I think that's true of a lot of other people. I'd love to see the glass community continue the road it has to becoming much more inclusive.
So let's move to beyond the lab. I have a few questions that I ask all interviewees.
Those were interesting questions. Those beyond the lab.
So what do you do at your spare time?
Well, I'm 81. And since I had that auto accident 10 years ago, my neck is very immobile. So that has influenced a lot of things. I used to be an avid golfer when I was younger, and I had to give up golf, obviously. Mostly now, I watch a lot of all the Atlanta Braves games. I've always been a big baseball fan. Writing this book has become a major part of my time too. Since I've gotten back into writing, and I plan to continue that. When this book's done, I'm going to be looking for another topic in glass to do another book on. So I'm open for suggestions. But at 81, most of your outside activities are pretty small. My daughter and granddaughter live with me, and a lot of my activities are really just interacting with them. At the moment, we bought a shed this spring, a big shed. It's 12 by 16, and we're converting it into a she shed for my daughter, which means we're insulating, putting up paneling, putting down flooring, etc. And that's one of the things that I'm doing these days.
What was your dream job when you were a child?
Again, I've been lucky because I combined my two dreams as a child into one career. I wanted to be a writer. I've always liked writing. I just enjoy it. It gives me a lot of pleasure. And the other thing was, of course, I was very interested in science. I didn't know what at the time. I actually was in high school. I was planning to go into chemistry because that was something I knew about from, you know, schoolwork and so on. And I actually went up to Rolla to a summer program in the summer after my junior year, sponsored by NSF. At that time, the Russians had put up Sputnik, a few years before, like 2 years before. There was a huge push in the U.S. to em, em, emphasize science and technology. So NSF was sponsoring these programs all over the country. And they had a program at Rolla, an 8-week program. So you went up and lived in a dorm for 8 weeks and they had courses set up for us and labs. And I got exposed to things like we did welding, we did aluminum casting. I still have an ashtray we made. We did some ceramics. We did all kinds of things. And one of my professors was a ceramic engineering professor. I actually went around to different departments talking to people about what you did in their degree, talking to professors, because I knew I wanted to go into science or engineering, but I didn't know what. It just was sort of a general dream. And the professor from ceramics convinced me that ceramics was a great way to combine an interest in both chemistry and physics. And he was right. And I decided at that point to go in ceramics. So at the time I graduated from high school, my dream was still to be a writer. I kind of put that on hold because I didn't really see it as a future. I was going to be an engineer, and which I became. But then when I got to graduate school, I discovered that you actually wrote papers and published them.
Yeah.
And eventually you could even write a book, and so I would say that my two dream jobs as a high school student were something in science and writing. And my career has been able to combine those to an extent that I would have never anticipated at that time. I would have thought it was one or the other, but in fact, it has been both. Again, luck.
So, two more questions.
Okay.
You have any regret in your uh, career, in your personal life?
I'm like everybody. I've always said I never regret things I did do. Can't think of anything I regret that I did do. I regret things I didn't do. You know, since I've been retired, and particularly since I started work on this book, one of the things of regrets that I found is, oh my, why didn't I study this? Why didn't I study that? Why didn't I make those glasses? Why did I not do that? As I find holes in the literature, as I do so much of my time involved in analyzing the existing literature, I find the places where they're missing information. And those are a lot of the regrets I have is, why didn't I do that? I could have done that. I even knew about it at the time. I just didn't for some reason. There are obviously all those things in my own life, Get really personal. There's that girl I didn't marry. But then I married the woman who became the mother of my daughter. And that's the greatest happiness in my life is my daughter. So I certainly I can't say I regret the first case because it led to the second. I used to tell students, they'd come to me and say, well, I've got 2 job offers. Now this one pays more than that one. And what should I do? And I always tell them, in life, you never have enough information to make the big decisions. You can decide what you want for lunch. Deciding what job you want to take when you've got 2 that seem somewhat equally attractive, you don't have enough information to ever decide that. So go with your feelings. And, in one case, I remember a young woman saying, well, I've got an offer from in Wilmington, North Carolina, and I've got an offer in Ohio. The offer in Ohio was $5,000 a year more than the one in Wilmington. So I should probably take that one, right? And I said, where would you like to live? She said, oh, I've always wanted to live by the ocean. I said, then what's your question? You know? Um, so, um, it's sort of like that old Frank Sinatra song, regrets I've had a few, but too few to mention. And I feel that I've been blessed my whole life. I had bad luck. I lost my ability to swallow so that I haven't had a bite of food or a drop of water in 10 years. I have a feeding tube in my stomach and all that. But, I was feeling kind of bad for myself when I was in the hospital until I went to rehab and saw all these people who were lost arms and legs, were blind. And I realized I just lost the ability to swallow. I can still lead a normal life. I'm lucky. And I've always taken that attitude, you know.
Yeah.
So I don't really have much in the way of regrets. I read that question. I really tried to think of anything that I really seriously regret, and I can't think of anything.
If a time machine existed, you would rather travel 100 years back or forward?
It's a good question, too. I've always been an avid science fiction reader. I've read, Lord knows, how thousands of science fiction stories and books in my life, and that comes up a lot. Um, I think I would rather go back. For one thing, I'm 80, so if I went back 100 years, I'd only be 20 years before I was born. And I think I could still understand the world at that point. I look at what the world has changed from when I was a child to today. When I started college, we had a slide rule. I don't know if you even know what a slide rule is. Um, it was I can't even explain it, but look it up. I think you'll find it interesting. This was before such a thing as a calculator. And we did calculations using log tables, um, and graph paper. Everything was hand plotted on graph paper. And I look at the world when I was young and today and the changes and think, now let's extrapolate ahead 100 years. And these curves continue to have a continually increasing slope. And I've got a feeling in 100 years, I would probably be so lost that they would simply put me into some kind of an institution for people who can't function in society. It'd be justified because I wouldn't be able to function in society. But I think I'd much rather go back to where maybe I was a little ahead of what the times were than to be so far behind that I could never really adapt to it. I'm having a lot of trouble staying up with computer technology since I retired because I'm not forced to use it all the time. As I told you, this is my second ever Zoom meeting.
Yeah.
If I were still working, I'd be having them on a very regular basis. But as a retired person, no. And so I don't bother to learn how to do it. Um, so I think that's sort of the answer. There's one last comment I'd like to make about glass science. In recent years, I was when I was in my 30s, there were a group of us kind of consider ourselves the young Turks, the up and comers of glass science world, and there were the established people in their 40s and 50s, and those people are all gone. And I think today, some of them have died more recently, but others further back. We don't really appreciate their contributions and what they did to get us where we are today. And in particular, a lot of these people were good friends of mine. People like Bob DeRamus, Connie Moynihan, um, oh, Adrian Wright, Phil Bray, um, um, Chuck Kirkjian, Um, and I think that one of the things that I would love to convey to your generation of glass scientists, don't forget to look at the old literature because you're duplicating a lot of it. Better instruments, but you're still duplicating it. You ought to go back and see what they did. I find today that if a paper is not listed in an online database, it's not cited, which means you're only citing the last 20 or 30 years worth of information. And I think there's an awful lot that you can learn from going back to the original papers and reading them. In working on the Germinate book, I went back to the first paper ever published on GeO2, 1937, where they made a Germinate glass, the first successful making of GeO2, vitreous GeO2. Before that, people had been unable to make a glass out of it because of the way they were trying to do it and so on. And I looked at that paper and I looked at the properties they measured. And their values were right. Their density was the same one we found today. Their refractive index, their expansion coefficient. In 1937, they made the basic measurements that are still correct today. And I think that you learn from those people. And don't forget that they are Newton said that if I have achieved much in my lifetime, it is because I stand on the shoulders of giants. And I think that that's something that, again, I'd like for your generation to recognize were these people who were the giants of the glass science world.
Sure, exactly, exactly. Uh, Thank you so much, Professor. Thank you so much for your time. It was a great pleasure talking to you. And thanks for the great jobs you have done, the great research, the great contributions you have made in the glass science. And I hope you enjoy the rest of your day.
Okay, thank you very much. Goodbye.
Bye.